Hey, ETH Denver. My name is Abdurrahman Omran. I'm leading the developer relations at Cartesi. Today, we are going to enjoy a meaningful discussion together. So, yeah, before we start, anyone heard about Cartesi before? Okay, nice. Majority is not, so that's why we are here. We are having like core contributors from Cartesi. Please prepare all your hard questions. They love deep technical discussions. So, yeah, first time to Denver. And I really like the city. I like people, the attitude, the vibes, everything. I don't like the weather, but yeah, everything else is really great. So yeah, first time to Denver, and I'm very excited to be here with you at ETH Denver. So what are we going to cover today? We are going to cover 4 segments about Cartesi. The first one is going to be a very high level overview about Cartesi. What is Cartesi? What we do? What we are trying to solve? And the second, we are going to go through a showcase. What are real-world examples that you can see, that you can build on top of Cartesi? What are the real use cases? And next, how does it work? And then we are going to go even deeper and see how can we technically, practically, step-by-step build on top of Cartesi. Okay? So, yeah, let's start with the first one. So, what I'm going to cover is the first high-level overview about Cartesi. What we are trying to solve as Cartesi Rollups is 2 main challenges. The first one is computational scalability, and the second one is programmability. How we are going to change that, or how can we solve this, how we are trying to fix it. Before talking about how we are fixing it, let me tell you a quick story. It's about a banana, not a blockchain. I'm going to use a very basic metaphor. Let's forget about blockchain for a minute and talk about banana. The banana doesn't have to be 10 times X just because there is a casino down the road opened and suddenly become very popular, right? And that's actually what's happening with the layer 1 blockchain. A lot of applications, a lot of users are competing for the scarce limited block space, right? And that's why everyone is competing for the same limited resources. And with the popularity of Ethereum blockchain, with the popularity of the layer 1s basically, the more DApps, the more users comes to the layer 1, the more slow, the more expensive it will be, right? So for an application to be viable, for an application to be meaningful, it has to hold itself in this war, in this resource war between a lot of DApps, a lot of users using this layer 1, right? And for that, you will find DApps, your new DApp that you deploy on that layer 1 competing with other popular DApps. They are competing for the same resources. They are competing and bidding for the same resources, for the same computational attention that node runners verify the network state. So why this is a problem? We believe this is a problem because everyone is looking for a global consensus. Every single DApp, every single user is looking for a global consensus for everyone to verify the same transaction, right? And that's, in our opinion, the more popular the network becomes, the more it becomes a huge problem. It's going to be slowing the whole network, making it more expensive, and at the same time, don't give the scalability that you need for your own DApp. And by that, like the network itself becomes gentrified and the innovation will be hindered. That's why we are thinking about something that should be more scalable, and that's what we are trying to solve. How we are going to solve that? We are talking about modular blockchain architecture. How? Like it's about modularizing the blockchain architecture that you have. We are talking about execution, about settlement and consensus, and specifically local consensus, not global consensus. So for Cartesi, we choose to go away from global consensus. It doesn't have to be everyone in the network competing for the same resources and everyone in the network verifying every and each single action for every app, right? So that's why it doesn't make sense to have everyone in the network, all nodes or verifiers, validating all transactions at the same time. In our opinion, we believe that every user, every DApp should be verifying only the transactions they care about, the rollup specific transactions, the application transactions they care about. That's where rollups that's where application-specific rollups comes into play, right? And with that, we are embracing the application-specific concept, the application-specific rollup concept, where your application will have its own rollups, and the network of your own application only will be verifying these transactions for your own dApp. With that, we can have, we can open the doors for a lot of new generation of dApps. Just imagine that if you can have this flexibility and this scalability, just imagine what's the opportunity that we can have here. So to recap this part, we are talking about Cartesi as a application-specific rollup solution that can run as a layer 2 on top of Ethereum or as a layer 3 on top of Arbitrum or Optimism. So if you are using Ethereum, you can use Cartesi to run on top of it as layer 2. If you are using Optimism, for example, as a layer 2 on top of Ethereum, you can use Cartesi on top of Arbitrum or on top of Optimism as a layer 3. Let's go back to the world computer analogy that some of us talk about Ethereum as a global or world computer, right? We think about rollups as the universal computer, something that's much bigger than the Ethereum itself. Ethereum enables that. Ethereum gives us the foundations. And this layer 1, you can think about it like a sun in the middle, and everything around it like a constellation, planets revolving around this sun, right? And one of these planets could be Cartesi. Like you can think about this as Cartesi rollup, about this as a Cartesi rollup. This is maybe something else, another rollup, and so on. So that gives us more flexibility to build a faster, more powerful, and more sophisticated dApps on top of the Ethereum ecosystem itself. That's the first one. That's the first challenge we are trying to solve, which is computational scalability. The second challenge we are trying to solve is the programmability. Before we talk about programmability and what we are trying to solve here in details, let's talk about the software engineering in general. Software engineering, it's been a couple of decades. Developers and engineers have developed many layers of abstractions, every layer on top of the other one. And all of these layers actually hides the complexity and the information of the lower layer, right? You can think about it let's look at this diagram. There is operating systems, tools, libraries, compilers, interpreters, and so on. All of these built on top of each other, starting from the base layer, which is the platform architecture itself, the operating system, the low-level languages, the machine code, the high-level languages, and so on. And on the top, you can develop your own app using these high-level programming languages. So why we should go and reinvent the wheel when we are developing for the blockchain? Why not we can use all of these tools on the blockchain as well? Because it's already battle-tested. It's been decades for engineers that have been using it, has been developing it, and that's what we are trying to do. What we are trying to do is just to bring the well-tested tools like Python, C++, the Linux operating system, and everything that it allows you to do with it, right? And that's what we believe in. We are trying to bring Linux operating system on top of RISC-V architecture into layer 2 optimistic rollup solution. And with that, you can just think about the opportunities that you can do on top of that layer. So with that, we can say hello to Python, C++. You can use your own database, decentralized database like SQLite or something similar. You can use Python to develop your dApp and to connect it to the smart contracts. You don't need to be limited to the limitations of Solidity or any of the existing development tools. You can basically use any of the tools and languages that you already know and love and you are already using on top of Linux, right? So yeah, with that, we are saying hello to Python, C++, JavaScript, SQL, and so on. This is a very quick example. How can you develop a very simple dApp on top of Cartesi Rollups? Most of you, you already have seen something like this. It's a Python script. With 3 lines of code, you can import any native or third-party library in Python. If you are using Python to develop your own dApp, you can use any native or any third-party library included into your dApp, and it's as simple as that. You don't need to reinvent the wheel. And that allows you to use something like image recognition. You can use machine learning. You can use any of these complex technologies within your DApp. You are not limited anymore to the limitations of the existing development tools. Yeah, so that comes to the basic question, which is what is Cartesi? And what is Cartesi exactly? It's a general purpose rollup solution. It's infrastructure for application-specific rollup solution. You can use it to develop your own DApp on top of it. If you are using Ethereum as your base layer, as your layer one, you can deploy your application using Cartesi on top of Ethereum. If you are using Optimism, Arbitrum, any of these language networks, you can use Cartesi on top of it as well. And it's EVM compatible, so you can deploy it anywhere EVM compatible. That's it from my side. That's a very high-level overview about Cartesi. What is Cartesi? Let's go a bit deeper, kind of like real-world examples. Show us some existing dApps, some ideas that might give us some inspirations. Also, like if you need to know more, you can check the documentation on our website. You can hear it from other developers that already developed some dApps on top of Cartesi. And this is actually like you can scan the QR code. You will find a YouTube list with everyone who developed on top of Cartesi. Very inspiring stories. And also, we are welcoming everyone on our Discord server. You can reach out to me also on Twitter. I'm Abdurrahman Amran, leading the developer relations at Cartesi, Omranik at Twitter. And we are here for the full event, like these 2 weeks. Find anyone with this T-shirt, myself, Carlo, Gabriel, Lino, Max, and Zach. You will find us everywhere. Just find us, ask any questions, and we will be happy to help and support you. Thank you, everyone. And yeah, let's get it back to Carlo.
Hey, how you doing, guys? Pleasure to meet you. I'm Carlo. I'm from Solution Architect at Cartesi. I'm going to talk a bit about real cool stuff, at least to me, that was developed using our tech, okay? If any of you guys have a question, well, feel free to make it, okay? So how can we use Cartesi? Basically, you can see Cartesi as something that enables you to do more on your Web3 application. So you can further decentralize what's currently impossible. So we have multiple really cool applications that use the blockchain, but the core of it is actually centralized. And that's because you don't have the tooling or the processing power to do it. We have multiple interesting games on Web3, and the really simple ones, you can actually express them, the game logic on smart contracts. But most of the games that need a bit more of context, of processing, they are actually centralized, and they just use the blockchain for financial layer. So with Cartesi, we expect to allow you guys to actually decentralize that logic as well. Also, as Omran said, we are bringing a lot of tooling that have been traditionally available for Web 2. And with that, we want to make sure that you can express yourself better on Web 3. And that's also another reason why you should be using Cartesi. And you can use all these traditional stacks. And finally, most of the developers, they are not used to blockchain. It's really a steep learning curve, right? You have to learn lots of new concepts, new VM, new language, everything. So if you can just use the stacks that you're used to in Web 2, it's much easier for you to get onboarded on making an actual decentralized application because you're using the stacks you're already used to, right? So let's talk a bit about the applications themselves. What's being built? So a first example that I really like, it's a game. And this game is called Dinder. And it's a nice example of these kind of games that traditionally would just use the blockchain for NFT layer and things like that. But the actual logic would have to be decentralized. So what's Dinder about? It's a mashup of an RPG game, like Pokemon, for instance, and a puzzle like Candy Crush. So basically, you have this battle in which you have your team, the other guy has this other team. You say, I want to attack this guy using this skill, and then you power it up by making a combo on a Candy Crush-like shared puzzle. And then the other guy does the same. You can choose to either attack him really hard or to just mess up with the board so he cannot do his combo. You have your own strategy. And it's a really nice game with complex logic. The game logic itself is written in Rust. And, well, it runs inside the Cartesi machine. So when you're playing Dinder, you don't have to worry about, has someone tampered with this random number? He's doing too many combos. I think he's messing up with the random number. Oh, well, I just hit him. I should have caused like 200 damage. Did he nerf my character on the back end or something like that? No, we have transparency. You can just run it in your machine. You can make sure that everything is all right. If someone makes a claim that's incorrect, you can just dispute it and prove it wrong. On Dinner, well, they use characters as NFT. And it's a really nice game. So it's under development. I think it should be publicly available soon. So they made this really cool Unity client, really beautiful with all the skills, really cool art. So it's a nice thing to check. Another really cool application, and this one is from DeFi. This one was born in F San Francisco. It's Nucleus. So I'm not sure if you guys check this out, but now and then we have like a DeFi hack for many reasons, right? And the Nucleus guys, they were particularly motivated by the Mango hack. So I'm not sure if you guys followed it, but basically on Mango hack, you have this lending protocol, and you can leave a coin as collateral. And this guy noticed that there was a really low liquidity, highly volatile coin that he could use as a collateral. So what he did, he picked up $5 million, he purchased it, it pumped the price a lot, then he comes to Mango and says, hey, I want 150 million stablecoins, or something like that. And then, well, Mango is a simple protocol that has limitations. What he did, went to our Oracle, what's this asset price? It was really high because he just pumped it. Okay, so this collateral is worth this much, get it. But it wasn't good collateral. If you try to liquidate it, it would be worth like 5 million, not 150 million. So what these guys did is, okay, how can we help this kind of thing not to happen? So they're leveraging the Cartesi machine. They just feed it the prices for assets, the volumes, and other relevant information. And with that, they just do a really nice analysis using NumPy and Python. And they make a model of risk for any asset. So this asset, no, it's really volatile, has low liquidity. If you try to liquidate a collateral over $10,000, you won't be good. So this kind of thing wouldn't happen. No, now you're trying to use a Bitcoin or Ethereum. No, great liquidity, it's awesome. Yeah, you can like put $100,000, 1 million. Yeah, it's going to work. So this is a really nice application, in my opinion. Another one we have that's really cool. So in some places, you use fingerprint readers for clocking in and clocking out, for instance. And in some locations, well, people mess up with it. What do? I don't want to work. So I just send someone from my team with a silicone finger. He clocks in, and he clocks out for me. And in these places, people start figuring out, okay, so people do this. Let's put someone watching them. So if they put a silicone finger, they'll catch it. But then something else happened. This guy started asking for bribes. You pay me a bribe, you're there. You don't pay me, you're not there. So this guy had this really nice idea of making a DApp for it. Because general Web3 applications are developed in a way in which the best way is just to cooperate and do the right thing, right? You're caught if you do the nasty thing. So what he did in here is he made this really cool application in which he has the input for it is your fingerprint. And then you have a C++ program that will process it with OpenCV and extract features out of that fingerprint. Cool. Now he feeds these features into a model he trained on Python, and it will tell you this fingerprint is for real, or no, it was spoofed, like someone put a photocopy of it, or a silicone finger, or anything like that. So I really like this example because it uses a lot of really complex libraries that have like millions of hours of engineering to become a reality and to do really powerful stuff. Another game one, but this one also has AI involved. So not sure if you guys play chess, but I'm assuming that at least some of you. So chess has this problem in which people just cheat. They don't play. You open an online chess, they go in there and they open a computer chess. Whatever you throw at them, they throw at the computer. And whatever the computer does with his infinite knowledge and processing power, they throw back at you. So you're not playing versus a human, you're generally playing versus a bot. So this guy, he's from our community, he said, okay, so let's change the game. You can play as a human, but let's focus on, I want to be a bot trainer. I want my bot to be the best chess player in the world. And that's his focus. So he made this ultra chess game in Python, and that's how it works. Basically, you submit your bot, you train your AI, you tune it, you improve it, so that you're king of the hill. And all the games, they happen inside the Cartesi machine. So if someone tries to tamper with the result or anything, you can just say, hey, this is not right, and dispute it. And it's a really cool game. This one, on the other hand, has a web user interface, traditional JavaScript stuff, not Unity. Another really cool application is one came from Indian guys, ETH India. So there's a lot of problems in India with insurances. Sometimes, for instance, it's different from where I'm from, but if you have a car accident, for instance, they can deny you the insurance because you didn't drive in a responsible way, for instance. Okay, and there's not transparency in that. They will just deny you and say, well, you're a reckless driver, and you don't have a say on that. So what they're doing on here, they're trying to bring transparency to this and fairness. What they do is they build this on Python. It's a DApp in which it feeds IoT data. So most cars today have this OBD2 port in which you can get all the data from acceleration, braking, all the stuff. And they feed this into a model inside the Cartesi machine, and it processes data, and it classify how good of a driver you are. So if you have your insurance denied, it's not because someone behind a wall in an office is saying so and you have no say on it and it might be unfair. No, it's actually transparent. You can verify the data is in there. You can run the model. You can check yourself. Yeah, you were a reckless driver, and that's why you're denied the insurance. So it's an example I like a lot. This one is really cool and still on this automated gaming. So these guys in a hackathon in Boston, they had this, well, I'm a sucker for old school games, so I like this one. They basically ported this Mugen-like engine for fighting games made in Go, ETH Go, and they call it from within Python. And they have these automated fights with crazy characters. So in this guy is the Kung Fu guy versus Pichu, but they have characters like a tennis player or a delivery dude, all the crazy stuff you can think of. And before the game starts, you can wager on one of them. Then the fight happens automatically inside the Cartesi machine. And then they pick up this fight simulation, and they render a nice old school graphics video for you to watch what happened in the fight. Kind of like MMA for video game people. So I think it's really interesting. And well, again, you got Linux, so you can run this Mugen-like emulator. You can hook it on Python for controlling it, for making the render video afterwards, all this cool stuff. This one is actually from Bogota. So generally when you have these NFTs, the certificate of ownership is on-chain. The content is generally not on-chain, and someone can swap your image because it's a link to a server or something like this. So these guys, they had this really cool idea, which they make procedural art on for these NFTs, and they use these really cool patterns that are fractals using a Mandelbrot algorithm, which is a really computation-intensive algorithm. And well, they did it in Rust. They're on a Linux server with a lot of computational power, so they did it. And turned out really nice results. So this was one of the images they generated, for instance. And with this kind of NFT, you don't own it, but you own it and you can prove you have the correct art because it's generated inside the Cartesi machine. If you want to retry yourself, you just re-execute it and you regenerate it and you see, yeah, I have the correct art. This one is more traditional IoT. So these guys are from Poland. And what they did is they did this decentralized parking application. So someone, might be the city hall, might be a DAO, might be whoever, establishes the zones of parking and the rates and all that stuff. You park your car, you interact with this and say, hey, I want to park here for 2 hours, something like that. Anyone can just go in there and check, oh, this guy has paid parking? Yeah. And he still got 1 hour, stuff like that. They made a nice front-end traditional with Google Maps, all this stuff. And inside the Cartesi machine, they build a logic using Rust. They have a SQLite database for storing all this information, for putting the new rules, like the new fares, for checking out how many vehicles do I have, how many spots do I have left, any statistics you might perform. And that's really powerful because We all know that it's a real struggle to deal with data on the blockchain. It's expensive. You don't have much tooling for manipulating it. You have some things like the graph to help you out, but you have to pre-index data in a particular format. So having a database on it, it's really powerful, right? And the front end was built in Vue, so yet another technology that they choose to use on the front end. We have many other examples. I was a bit worried about the networking, so I didn't add this. But one crazy dude from our emulator team did something which, as a nerd, I appreciate. So will it run Doom? And yeah, he put real-time Doom inside the Cartesi machine. So I think it's a really nice example of the things you can just do when you have a Linux machine available for your decentralized logic, right? If you guys got any ideas, got any doubts, want to discuss if your idea is viable or not, if it fits, kind of adjust the architecture, anything you have, well, we're here, we're available, and we'll be really, really pleased to talk to you guys, okay? That's my part. You have a QR code in there for Discord, if I'm not mistaken. So yeah, hope you guys have a really nice event, and well, have fun. I'm going to give it to my colleague Barros now.
Hello. Hello, guys. Gabriel, I'm lead developer advocate at Cartesi. I'm here to give you an idea of how everything comes together. Of course, by the end of this, we're probably going to still have some questions and some doubts. It's such a short time to explain everything. But hopefully, I get you intrigued to talk to us. So, quick rundown of what I'm going to say. I'll go back to rollups, app chains, talk a little bit about the Cartesi machine, how all of that is possible, the importance of fraud proof in the system, and by the end of it, I'm going to show you a little bit the APIs we developed to make it possible for you to do your DApp. So rollups. Rollups are a stab at a blockchain trilemma. We all know that. It's the stab at scalability, trying to improve the TPS, computational power, and by the end of it, really trying to make it cheaper to process things, right? And the idea is to make it so that, in a way that you don't compromise security and decentralization. And the focus really is on computation expansion. Okay, what about app chains? So when people are talking about rollups, we like to go back here. It's a little bit what Wormran said before. So on Ethereum network, you have this massive network where you add computers to it and you improve on security and decentralization. However, you cannot really expand its processing capabilities, not really. We can strive to do it, but it doesn't scale really well. But with app chains, it's different. So you have separate network-like rollups where some computers might be present in two different apps, but they are logically separate. What it means is, if by any chance, let's say DApp is super successful, it's not going to steal resources from the other dApps. It's not going to do the network eviction that we've seen so far happening in Ethereum. So for those of you who are older in the space, you remember by 2016, 2017, we had a bunch of games showing up at L1. But with the DeFi explosion, there was no games anymore because it's too expensive to do anything on a game. And it doesn't make any sense. So with the idea of having a DApp chain, you're guaranteeing that your application is still going to stay healthy throughout time as long as people are interested in it. And you're not going to be bound by what happens to the other applications that are using the same technology as you. So the ecosystem stays healthier for longer. Okay, what about the Cartesi machine? So the computer you have right now, it has one of these architectures, AMD 64, IA32, or even M1 from Apple right now. And even your cell phone, you have like an ARM. processor. These architectures, they are very capable and very powerful. They are so that they are enough for you to have an operating system running on it, right? And that's really good, because that gives you access to a lot of resources. You can have files, you can have network communication, you can have sockets, you can have a bunch of stuff that we forgot that exists when you're programming to the ETH, because it's more or less like a very powerful calculator. But that hinders your ability to do things. So in that sense, Cartesi used RISC-V, which is an open source version for hardware. It's an open hardware architecture, and we did an emulator on top of it. That means it's possible to run Linux, and with that, now you are able to run anything really on top of it. You still don't have access to the internet. That happens a lot. People often hear about Linux on the blockchain, and they're like, okay, can I connect to servers? Not really, because you're still bound by the blockchain data availability. However, now you can have access to files, you can have access to several types of databases inside. You don't need to reinvent the query language just to make sure like you can cross-reference data that is stored in the hash table of Ethereum. So that makes it much better to develop complex applications, really. And that also means that you have a very capable CPU that gives you abilities to do things that previously it was unheard of. Like, you cannot really process an image, you cannot really decrypt things, you cannot really... it's very limiting to program on Solidity right now. And that works because you can have fraud proofs. So I told you that we did an emulator of RISC-V, but that's not compatible at all with EVM, not at first, right? So what we did, we actually ported the emulator as well for the EVM. So we have a set of Solidity contracts that represents the RISC-V machine. And any instruction that can be computed off-chain can be computed on-chain as well. So what we needed to do, and we did, is a process called verification game, where let's say you were playing a game for a week. Now it's finished, and somebody is complaining something about the game. They're saying somebody is doing something nasty. You can just do a search, a binary search, basically, on the whole process and find a single CPU instruction and put all the data necessary for that on-chain. It's super cheap, by the way, and do one single CPU instruction cycle on-chain and verify who's telling the truth. So it's very simple thing, actually, to verify the computation you did outside with all that thing that we are just saying, like with OS, abstractions, Java virtual machine, if you want to, databases and whatnot. And this is kind of like how it looks like. So you have a set of nodes here. That includes the Ethereum node, because we still need to have access to data. You're still bound by the data availability problem. But then you have other nodes from Cartesi here. And your front end, any kind of UI really, you connect using some of these endpoints. And from within the Cartesi machine, the Linux machine we're talking about, we created this API abstraction here that makes it much easier for you to integrate with the outside world. Let's take a look at the inside first. So from the inside, we have the API I was talking about. It has just a few endpoints that you need to know of. The documentation is super nice for that. First, you need to be calling this endpoint over here that will tell that you're ready to process the next transaction. So this is still a state machine. So whenever you have a new input, a transaction, it wakes up, processes the information, and it finishes. So it's a loop where you're always calling finish at the end to tell the system that you're done. You're waiting for the next query. Now, you have two main states of how to process this new information. So whenever you have Ethereum call, for those of you who are more familiarized with JSON RPC from Ethereum, basically you're waking up the machine to process something, but you don't intend it to store it. You don't intend to have a straight transition. So that's why we have inspect state over there. So if you need to query about anything of the state of the machine, you can just call inspect state. From outside, you're going to see that. And from within the machine, you need to be aware that the machine is going to revert. So let's say you have a counter there. Whenever you have a call, you add 1 to it. That thing is always going to be 0 and a 1. You can't change state when you are in that particular set of the state of the machine. Then there is advanced state. That's just like a normal transaction on EVM. That means that you need to be cautious, to have caution, because if you break your DApp, if you break your contract, might be a Python contract, might be a Java application acting as a contract, but if you break that, then your DApp is gone, just like the EVM. And then you have the 3 main types of outputs over there. So let's start with the simpler one, add report. So when you add a report, it's basically an ephemeral information. It's like logging information in your application. It's something that is only going to show on your node. Of course, if people reproduce the same code as you, they're going to see that as well, but it's not tied to the state. Then you have notices. Notices are like Ethereum events, but with a special twist to it. So an ERC20 transfer, it has an event to it that you can verify by running the Ethereum node. But if anybody gives you the payload of the event, you cannot verify that that's true unless you go back to the transaction that created it and verify by running it again. However, notices here, they have a Merkle proof to it that is tied to the state of the rollup. So whatever information you get from a notice, it's just a string, really, of data. You can verify the veracity of it by having the Merkle proof to that. So it's an Ethereum event with a special touch to it. And finally, we have a voucher. We call them vouchers because rollups, they need the 7-day window of fraud detection, and so people can open disputes. So you can only do transactions really once the state is settled and people agree that there's no changes going to happen anymore. So you create vouchers, basically transactions, and people can claim those vouchers once the state is finalized. So these are basically, this endpoint is basically the way you're going to interact back with the Ethereum network. So somebody wants some tokens and they need to withdraw. It's going to be our ERC20 transfer voucher that they're going to claim later on. Okay, these are from within. These are what you need to know when you're writing your contract. From without, there are the APIs that we're talking about. Let's just go back there for quick. The JSON RPC and 2 APIs for the Ethereum node over here. The JSON RPC is basically for the data availability. So you call on a contract, a rollup contract on Ethereum, the function add input. It's basically just to register information going inside the rollup ecosystem. It's not going to do anything, really. It's just so we can agree on the information there. That is what synchronizers have been doing for us in the other rollups, by the way, so you have as a comparison. And then you can query outputs from the graphical API. The outputs are the reports, notices, and vouchers I was talking about earlier. So whatever you produce from inside, that's how you get from the outside using the graphical API. Finally, you can have the inspect state. Basically, you are free to do with that whatever you want. So you can register sub routes to the inspect state. So it's from within the application you define those. So you can really do something like a REST API if you wish to do so. And those are going to come as a high-level inspect state API call from the outside. And finally, you can execute voucher, the thing I was talking about. So whenever a voucher is already valid and settled, you can just call execute voucher. Then a new Ethereum transaction is going to happen coming from the rollup address inside the Ethereum network. I know it's a bunch of stuff, but we're going to have 5 to 10 minutes at the end of the presentation to talk about these, and you can ask questions. So for the next session, Luna is going to go through a programming DApp with you, and you can just get your Linux, because that's the best for this. Thank you. Aqui passa e esse botãozinho é o laser.
Hi there. So I'm Lino from Solution Architect team. And we are going to, just a quick start on how to get into Cartesi. So now you should go to your terminal, and your Unix environment works, but we advise you to use Gitpod. There's a link on our GitHub repo. So in this exercise, we're going to run the EchoPython, which is a very simple example. And we're then going to make some changes and see how it behaves. And yeah, so that's for today. So this will just clone the repo, build the Cartesi machine, and start the Echo frontend, which is a web interface. So you just, if you're using Gitpod, it will be automatically clone the repo for you. But it's just, you have to go to the rollups examples and the Echo Python example. And then from there, we'll build the image which contains the Echo Python code. So we use Docker to set up all the environment. And the first thing, you have to build the Docker image with the Cartesi, with the Echo Python code. And then you can start the backend, which starts all the infrastructure for run the Python. So has all the node, the part that reads the state on the blockchain, also what handle the information. So we just Docker compose and put all the configuration files, and it will run deploy a local hard hat chain. So yeah, you can test everything locally, and then it takes a little bit of time to set up. But if you do this, it's in a couple of seconds. It should work. And then to the front end, you just change the directory to start a new terminal to the Echo frontend. You have to install the dependencies. All of these instructions, by the way, are on our GitHub repo of rollups examples. So you have to use yarn to get all the instructions, all the dependencies. And then you can start the front end. So by now, you can it will start the web interface, and you can send the transactions. On the other side, all the Cartesi rollups node what they are running. So the hard hat local chain, the inspect the inspect server, the graphical, all those interfaces that Gabriel said, and you can see that it reads the state of the local chain, and then gets the output from the graphical. So yeah, when it reads, you will get the response. So one thing that's very important when you are developing with Cartesi, since it starts a whole environment using several Docker containers, it's important that you stop and remove the volumes and the containers. Otherwise, the volumes won't be removed, and you have old information on site. So every time that you do, you have to Control-C it and then you have to stop the containers with Docker compose down -v. So now it's Control-C. And then you have to just put down -v, and it stops and removes everything else. So now we're going to make some changes to the EchoPython, and then we're going to see how it behaves using a console version of the front end. So yeah, just make a simple change. We're going to make change how it answers. So now here I'm copying some of the functions. So all the informations that when they get inside the Cartesi machine, when you're going to process, they come as a hex encoded. So in order to change and to see them as strings, you should decode it from hex. So that's what I'm doing here. And then we're going to change the string and see what happens. So, and now we're going to change and add a little, change the string there. Then we have to hex encode it again. So cave echoes, yeah. And we have to do the reverse when we are outputting the message. So I have to encode as a hex as well. And then you have to start it again, the backend. And you have to rebuild, since I changed the code, I have to rebuild the Cartesi machine with the new code. So it's just run the same command that we ran using the same docker build x bake load. It should be fast since it's a small change, just to put the new code there. And then we can just after we can start again the rollups framework. Yeah, it's just start, and yeah, it should be ready to go. Now we are going to test the changes with the front-end console. So we go to the front-end console. It's this one is more general for you to interact with the application because it has several other commands inside. So when you're developing, maybe this one's better, and then you can build the beautiful framework using web interface and everything that you want. So just yarn start and send an input to the rollups framework with the payload. And you can see put anything that you want. It will convert to hex to put inside the local chain. Just send another one, and then we can check the changes. So just list, it's notice list, and you can see the cave echoes hello. Yeah. So this was just a quick presentation on how it works. We have other interface that you can test, like the vouchers, all the other languages, and you can always come to see us. And if you have more doubts on how to build, we will be available. So yeah, now we got some time.
So guys, any questions, doubts, suggestions, anything? Okay. Leon.
Of course, I'm scared to.
Right, okay, I asked a billion questions, so maybe there will be a lack of context, but okay, I guess my main question is how does, when you have application-based validation and nodes, how do you reach consensus on global state things like tokens?
Okay. So basically, as we said, we have this platform in which you can deploy your application-specific rollup wherever you want. So the resources that you put in it are associated with the underlying chain. So if you're running on Ethereum, you will be handling with Ethereum NFTs, this kind of stuff. And those live on the underlying chain for their consensus, all this stuff. On our level, which is the Cartesi level, what happens is that you don't need local consensus. So it's not like I have 10 people validating this application. If 6 of them want to do something nice, they will do it. That's not how our security works. The way our security works is you need to trust that at least one validating party will enforce the correct result. And why is that? Because the way our system is secured is when you have someone that makes a claim on chain, they basically pick up the Cartesi machine state and they build a Merkle that index it and they put it on chain, the root hash. And they say, at this point, this is what I got. Any of the validators will do the same stuff. They will check, okay, do I have the same root hash as this guy claimed? Yes, nothing to do. It's an Optimism rollup. If not, then we have a dispute. And how do we settle the dispute? We have this protocol called verification game, which is being used for other projects as well. But basically what happens is the Cartesi machine needs to be deterministic so I can reproduce computation. So if I'm not agreeing with you, it means that at least in one point we did something different. The protocol identifies what's this first point. What's the first instruction of RISC-V execution in which I had the exact same state as you, but after doing it, it can be sum two members, or a subtraction, or write a value member, any instruction. After that, we don't have matching signatures anymore. That's the first part of the protocol. And the second part is, well, we had a huge effort on implementing a Cartesi machine emulator on chain. So once you reach this single instruction in which you don't agree, then you're actually being secured by the underlying chain. That instruction is executed by its own chain emulator. So if it's Ethereum, it's going to be thousands and thousands of nodes. And they're going to have the consensus on this is the hash of the Cartesi machine after executing the single instruction. So you're right or you're wrong. But it's not those 10 validators or 20 or 30. It's actually the entire Ethereum community or whatever blockchain you're using saying you're right or you're wrong. Okay? I hope I answered your question, not sure. Yeah, keep trying. So,
but if anyone else wants to ask something.
Yeah.
Okay.
Sure. Yeah, just hold on for me a second.
So when it's the consensus protocols running in the Cartesi machine, is it across all, like the Cartesi rollup across all of Cartesi machines, or only on the app chains?
Okay, so as we said, the point is that how can we remove the constraints on processing? So I have a computer. It only has so much processing power. If I try to validate everything that's going on, either everything that's going on is going to be tiny, or I'm not going to validate everything. So the way we chose was, okay, so you choose what you're validating. And a Cartesi node only validates a single application that you're interested in. So this Cartesi node for this specific application will look for this special smart contracts of our framework. And there are certain transactions they will look for. Like there's a new input for this application. Okay, I'm going to react to it. I'm going to feed it to my Cartesi machine. I'm going to step on it. And when someone makes a claim, do I have the same hash? Yes, I don't have to do anything. I don't, then I'm going to interact. In the logical sense, you can be a single validator because you're a validator giving your address. But physically, you can have a cluster of machines. So you have a server that's validating a single application that's really demanding. Then you have another server using the same wallet, so you're the same validator, but it's validating much lightweight applications, so you can have like 5 or 6 applications. I have a really high volume game that's pumping lots of users. Well, maybe I would need like a really large server just for it. So it depends on the application in the end. And again, since you don't have to validate everything, you choose to be a validator for application or not, you can manage your resources.
Okay, and just to follow up on that, like if you have like 2 different DApps running on a Cartesi, so what prevents like double spending, let's say, of some token on like both?
Okay, so that's a great question. So what happens is the execution environment is the Cartesi machine itself. So for your DApp, the reality is what's on that Linux server of yours. How do you interact with the outside world? So basically, in the framework, there's a special smart contract called the portal. And what's the portal? The portal is a bridge for assets. So whenever you interact with the portal and you deposit some asset, like let's say you're on Ethereum and you deposit Ether, you get a special input on the Cartesi machine to handle. That's going to say, hey, X deposited Y Ether. Handle with it. You might save it on a database. You might award him a token because he was purchasing a token, an item, whatever. It's up to your logic. But that asset is in that portal, and that portal is from your application. Now you say, OK, great. So we have a way in. What's the way out? So as Bah has explained, one of the possible outputs in the Cartesi machine is called a voucher. And what's a voucher? The Cartesi machine needs to be isolated because it's deterministic. So you cannot directly interact with internet or a blockchain or anything like that. But still, it's interesting for you to interact with the blockchain. So that's what vouchers are for. So basically, you set the transaction you want to execute. You cannot execute yourself, but you pack it on this voucher. And then someone on the outside can enforce it. So they submit this voucher into the framework, and the smart contracts will check things like, OK, so this is going to transfer, for instance, Ether from the portal to you, because you're allowed to withdraw 5 Ether, or this NFT, or some resource. And that's where double spending comes in. So how do you make sure you don't have double spending? OK, the answer is the voucher can only be submitted and executed once that computation is final. So it's a rollup solution. So once you roll up the state, you have dispute period. There can be disputes, there can be no disputes, but after it's settled, in that moment, you have a proof that's generated associated with your voucher. And that proof is validated by the framework when you try to execute it. So if you try to execute a voucher that it's not final yet, like I want to withdraw this item. Yeah, but you cannot because it's not final that you are awarded this item. It's still in the dispute period. You're not going to be able to do it. Another thing is, OK, so I have this voucher. I submitted it. I'm going to submit it again. You're not going to make it because these smart contracts also keep tab on the vouchers that were already executed or not. So I have all these validations to make sure that when you execute a voucher, you're actually entitled to doing that action. It's valid. No one submitted it before. No, there's no double spending, anything like that.
OK, thank you.